So this is lecture 4. So we're halfway through in our program on geometric data analysis. And today we're going to talk about geometric deep learning. Okay, and I assume that most of you are interested in that because given your choices in the list of projects, it seems to be a project that is raising interest. But let's start just with a recap of the previous lecture and why we would like to do geometric deep learning, like deep learning on graphs, on surfaces, etc. So, I mean, what we've seen last week in the lecture on graphs is first that the curse of dimensionality means that you cannot hope to make meaningful statistics if your samples are completely independent random Gaussian variables like white noise. Okay, there is no structure. The matrix of distances becomes completely gibberish. So basically, all advanced methods in machine learning, either implicitly or explicitly, try to leverage the structure of the data. Okay, try to do meaningful things when your data has some intrinsic structure, like either it is clustered or it lays along the low-dimensional manifold in a high-dimensional space. Okay, and this is a hypothesis that we always make. You know, like whenever we deal with natural languages, we assume that it's not just a monkey typing on a typewriter. Whenever we deal with musics, we assume that there is some meaning, that there is some structure behind the music. And obviously, whenever we do image processing, we assume that there is interesting signal that we try to separate from the noise. We try to interpret the signal. And to do this, usually you need to unwrap somehow the manifold of plausible data samples. Okay, and to be clear, here in those first lectures, I'm like in the machine learning mindset. Manifold, it's not very rigorous. Okay, we're going to see next week what mathematicians mean when they talk about a manifold. And definitely, I mean, real data sets do not lay along the real manifold, a continuous space, etc. Just a nice word to say that we hope that there is a low-dimensional structure somewhere, but maybe not smooth, maybe not with constant dimension, etc. So then what we saw as a motivating example is that graphs, they capture local neighborhood structures. So if you're given a real graph, you're explicitly given a set of samples and a set of edges that tell you, okay, this sample is definitely close to this one. And if you're just dealing with a high-dimensional point cloud, then maybe you can use a k-nearest neighbors graph for a good metric to capture this local structure. And this is what we see here. I have this kind of Swiss roll two-dimensional data set embedded in 3D. And by computing the graph of k-nearest neighbors, if k is not too large, I only capture like intrinsic neighborhoods without making jumps across the 3D space. So I can hope that if I have enough sample and if k is not too large, I can try to unwrap and understand that under the hood, it's just a two-dimensional space. So I can hope to do meaningful statistics. Okay, so that's the motivation for doing graphs, or one of the motivations for doing graphs. But we've seen that in real life, when you're given a graph, usually you do not really know what to do. Okay, because you're just given a soup of edges and vertices, or you're given a super large distance matrix, and untangling this soup of edges to provide a global understanding of your data can be very hard. So that's why last week I tried to show you simple archetypes, just simple toy example, simple intuitions to let you see that, okay, maybe graphs are not always grids, but maybe you can try to make sense at least of local neighborhoods. So we saw that cliques, so very highly connected subgraphs, are in a way like balls with positive curvature. Then you have grids, which are like planes, flat curvature. Okay, these are the graphs that are easy to deal with. And finally, you have trees that are a bit like saddles with negative curvature. And it's an intuition that we're going to develop more next week. So, okay, and we've seen definitely that this is tied to a continuous understanding. You can try to make like toy models of what happens that are both discrete and continuous. Okay, like those are just, I'm going to try to provide you with as many examples as I can, especially next week. just so that you understand that all this vocabulary about positive, flat, negative curvature, it's nothing mystical, hyperbolic, it's nothing special, just like complex numbers are nothing very difficult. These are all objects that exist in the real world and make sense. So, okay, then we saw that if you wanted to go beyond those simple archetypes, maybe you needed some kind of embedding methods, try to visualize your data. And this is what we saw during the lab session. So, and this is an important lab session, like it's probably the most important lab session of all, because UMAP is really an excellent tool, excellent documentation. I think it's like the gold standard of what you can do as an academic researcher to influence a research community and provide good value. So, I encourage you to actually go through all the UMAP documentation to see how it's done. And we saw that, okay, it's possible to visualize like toy data set, like the set of integer numbers from 1 to 8 million with p-adic valuations. But most importantly, UMAP currently is a mainstream method, for instance, in some areas in biology, because it allows people to visualize data samples. So I don't know if you've heard about flow cytometry, but it's really interesting technology where essentially you take a sample. I don't know if you put it in the mixer, but at least you put it in solution, and then you put it in an imaging device that's going to flow one cell after another, and for every cell, tell you the level of expression, like of some proteins or some genes. But what I understand is that you end up with a super large point cloud where every point is a cell, and every feature, like every column in the data set, is the level of expression of some gene. And so it allows you to understand the diversity of a real biological sample. And if you do that, like for mice at different stages of their life or in different places, you can try to visualize what's happening with UMAP, and usually you can see differentiation happening, these kind of things. So, I mean, strange, incredible data sets that people are able to manipulate thanks to those very advanced topological data analysis tools, actually, UMAP. So, big success. Now, okay, that's all well and good, but as you know, since 2012, we have grown used to using convolutional neural networks. So maybe in this class, I'm going to assume that you are maybe a little bit familiar with how you train a CNN. So could you just raise your hand if you actually know how it works? I know maybe you're in the MVA, but not taking any class about deep learning. I have no idea. Okay, so not everyone actually, it seems. Okay, so I try to not assume too much. Okay, but at least what we saw in the very first lecture is that basically people want, for applications, especially in computer vision, people want to define a pyramidal convolutional architecture where you concatenate convolution steps and like subsamplings, upsamplings, and like pointwise nonlinearities. You end up with a huge model that is parameterized by a collection of convolution filters. And the whole game is to optimize the weights of those convolution filters by essentially gradient descent on some kind of reconstruction error, like a classification error, some denoising test, etc. So, I mean, that's what we do. And definitely, I mean, the reason why probably you're listening to this is because there have been successes in image processing over the last decade, and everyone is curious to know how far we can extend those things. So now that we've seen that, okay, the technology of convolutional neural networks and images is definitely quite mature now. You can use it in production, etc. It's a natural question to ask if we can extend this methodology to other types of description of signals and images. And what we saw in the first lecture is that even just looking at a medical image, you have at least 3 levels of description, like, pixel grid, anatomy, or functional organ. And that those 3 levels of description, if you take a big step back, they correspond to different ways of grouping pixels with their neighbors. You can either group them in a square neighborhood, you can group them in kind of in a segmented tissue, only let points interact with points that belong to the same tissue, or they correspond to a kind of graph, maybe a biomechanical mesh. or at least something that comes from expert knowledge, where you have nodes and you know that some electric signal is sent from one place to another. So I mean, it's a natural question. We've seen that step 1, now it's mature. What about steps 2 and 3? And so today's lecture is going to be about presenting this active research topic, where we try to extend what we do with CNNs to other domains, other kind of non-Euclidean domains. So there's going to be 3 steps. The first one is that I'm going to be clear, honest with you, that geometric deep learning is not at all a mature field. Maybe people from the outside, you can be very optimistic. You say, okay, deep learning is major field, geometry is a major field. I mix the two, blam, I get miracles. No, it really doesn't work like that. Okay, we're going to see that. We can try to define convolutions on graphs and point clouds, but immediately you find problems. Like, it's not that easy at all to make interesting architectures on graphs and point clouds. So it's a pretty stimulating environment for everyone involved, for all researchers and all that. So, I mean, the literature is definitely blooming, it's interesting, but it's very hard to tell you what works, what doesn't. First, because the field is very wide, and also because the benchmarks are very questionable. So I'm going to try to tell you why those benchmarks, why it's very hard to take papers at face value. So because it's so hard and because all of this is so new, when preparing the lecture, I decided to, I thought that probably the most interesting thing for you would be to listen to some maybe personal experience feedback that I can give to you. I've spent 2 years doing these kind of things, both on protein docking and on lung registration. And I think, I had some kind of a balanced perspective on all that, and that probably you'd be interested by that. Finally, after talking about doing deep learning on graphs and point clouds, we're going to ask ourselves, maybe we can try to learn the graph structure, instead of using it as provided by domain experts or as found in the data. So we're going to talk briefly about dynamic graphs, autoencoders, and transformers. And at the end of the day, as a conclusion, we're going to see that this is all a continuous spectrum of methods, of models, of fields, actually, and jobs. And, personal perspective is that, it's very diverse, it's very interesting, and you shouldn't try to all go in the very same topic, to work on the very same models. It gets boring quickly, and basically different problems require different solutions. So I strongly encourage you to take many different lectures in the MVA. Try to look around, read many different things, not just about a topic that seems trendy. So let's start by saying that geometric deep learning is a field which is deceivingly not very mature. So first, what is a convolution? We talked about it in the very first lesson, in the very first class. Convolution, it's just a way, at least on grid images, it's a weighted average of neighboring pixel values. So kind of a cheap generalization of the product A times X, but that makes sense on images. So you have an image, a grid of pixels, you have a convolution filters, phi, and phi convolve with X. It's a new image, like essentially it's new pixel values on the same grid that are computed where for every pixel you take a weighted average of its neighbors. So here, a trivial filter where you only look at yourselves, but then we've seen that if you put weights on the neighbors, then typically you blur things, you destroy high frequencies. And most interestingly, if you allow yourselves to use both negative and positive weights, you're able to define edge detectors. So, and once you start to have edge detectors, you're able to do interesting things with images. So that's the basic idea. And then, okay, we saw that you could combine them. You can do a lot of things. So what is a convolution on grid? It's something that is cheap, that enables pattern detections and texture analysis, and which has very proven track record since the 1960s. Okay, people have been studying those architectures not since 2012, but since at least the 1960s, with experiments on gas and these kind of things. So, I mean, convolutions and subsamplings are the bricks that power Gaussian blurs, things that you have in paint, edge detectors, Laplacian pyramids, wavelet transforms, or JPEG 2K compression, and now convolutional neural networks. So very appealing. And so now people thought, okay, we can do it on images, maybe we can do it on graphs. And that's what we call doing message passing convolutions on graphs. So what's the idea? Here, I take just a very simple image, something like MNIST. And we've seen that, if you look at the equation, convolution is what happens if I replace, so the pixel values, I call them X, and the field values are called phi. And convolutions are what happens if I update the value of every pixel at location ij by a sum of the neighboring pixel values, like x of a minus k, j minus l, you go around, with weights that are just given by your small array phi. Maybe it's a 5 by 5 array. So that's simple. And you look at that and you say, okay, just making weighted sum over my neighbors, I can also do it on a graph. So let's do it. So here it's kind of a graph MNIST example where people have just computed superpixels on the MNIST data set, and gave them value here. And it's a k-nearest neighborhood graph. So here you can kind of see that it's the same image of 5, but in a low downsample graph version. And you see that, and you say, okay, that this pixel, at least according to my graph, is neighbors to those other superpixels. Okay, and so what I can do is to update the signal value on my graph at this node I as a weighted average, or as a sum over all points k, all nodes k that are neighbors to I, of, let's say, a general function phi that takes as input the pixel value at node I, the pixel value at node k, and maybe some kind of features that live along the edge. Okay, so, and it seems simple. If you just say, it just looks like a very innocuous generalization of what we can do on grids to what we have on graphs. And okay, so that's for convolutions. And then we also know that if you want to do interesting things with convolutions, you should combine them with up and down samplings. And graphs, it looks like you can also do the same thing. Okay, right? If I have a graph, I can downsample it, making k-means in the graph, something. And then combining both convolution layers and downsamplings, I should be able to define graph convolutional neural networks. So the promises of geometric deep learning are that we're going to do deep learning, but with a structure that best leverages the intrinsic structure of the data set. So maybe we're going to work on point clouds or surface and volume meshes. And instead of using the extrinsic 3D distance, I'm going to use the intrinsic distance on the mesh. So maybe I'm going to be able to move the fingers on a shape because two fingertips are far away from each other according to the intrinsic surface distance, but maybe too close together according to the 3D space. Maybe we're going to be able to work with molecular graphs, with proteins, and do things about social and communication networks. So that's the pitch, but unfortunately, things are not that simple. And why? That's because you have at least 5 big problems with the ideas that I just presented. So the first one is, how do you deal with the lack of orientation on a graph? Okay, so basically, we've seen that convolutional neural networks can express edge detectors. And actually, if you make experiments on trained convolutional neural networks and you try to analyze what happens in the first few layers, you definitely see that, at least for networks that are trained on ImageNet or medical image dataset, CNNs, they use this type of power. Like, they are going to learn edge detectors in the first layer, and at layer 2, 3, they're going to learn something like curve detectors. So those are images, I mean, as always, if you're interested in where the images come from, you can click on the links. You can download the slides and click on the references. But like, those are visualization of the convolution filters that you find, I think, in layer 3 of a trained ResNet. And you see that, okay, for instance, this neuron, so this channel in your big neural network is something that's going to fire whenever you find a vertical edge, which is like bright on the left and dark on the right. This neuron fires when you have something which is maybe darker on the left, bright on the right, etc. Okay, and so it's something that we've known for a long time, that those CNNs use all those edges and curves to try to capture something about texture and the patterns of our images. And so we'd like to be able to do the same thing on graphs. But the problem on graphs is that you do not have a clear notion of left and right. For instance, if I take this very simple grid graphs, that just looks like an image, but if I do not attach any features to my edges that could encode that this edges goes upwards, this edges goes rightwards, then using this kind of formula, I will only be able to define isotropic filters. My convolution is only going to be able to distinguish between neighbors that are like one-hop neighbors, two-hop neighbors, three-hop neighbors. So out of the box, with a naive definition, I'm only able to define those kind of radial filters. So immediately you see that we're losing a lot of expression power, and expression power that was actually useful. So, okay. You see that it's complex on a graph, and you have theorems, from topology, from geometry, that tell you that there's not going to be a simple answer to this problem. So I don't know if you know about the Unreliable theorem. Okay, so it's a theorem that tells you that, okay, on a plane, it's easy to define a globally consistent set of 2D coordinates on the sphere, a globally consistent 2D frame. You say, okay, basically, we move around a set of orthonormal vectors, UI, VI. You go and you say, okay, this is right, this is left. Like, you can define a convention. But now what happens if you try to do this on a sphere? And if you try to move around a globally consistent base, UV on the sphere, you're going to find that at least at one location, you're going to have a problem. Okay, and this is what is represented here, kind of round head that you try to comb, because orienting, saying that this is right, this is left is a bit like combing a surface. You have a vortex, like a point where it's not continuous. So maybe here it's locally consistent on a local neighborhood, but just, for topological reasons, you have at least one point where it's problematic. And so we see that on the very simplest surface, which is not the plane, immediately it becomes non-trivial. So what about complex surfaces, and never mind about graphs? So it's still problematic. Then problem 2, how do we deal with varying sampling densities? Things that we take for granted with images is that if I get an MRI slice, then it's sampled homogeneously. I know that my voxel size, my pixel elements are small cubes with 1 millimeter by 1 millimeter by 1 millimeter size. But when you're given a graph or maybe just a surface mesh, you have no control on the sampling density. So maybe it's super inhomogeneous. And so it's a common joke, at least by Keane and Crane, about 3D geometry, is that hell is other people's meshes. And like hell is other people. Okay, and it's something that rings true to most people who have worked with meshes, that whenever you download a mesh from someone, you say, oh my God, how on earth are they able to do anything with that? Like maybe from a graphics perspective, it looks fine, but whenever you try to do processing, you have strange non-manifold meshes, triangles that are completely nearly flat and all that. So, it's a common problem. It has been studied for decades in some fields, like 3D geometry, and people have come up with very interesting ideas like intrinsic triangulations. I strongly advise you to look at these papers, incredible math, in their incredible techniques. But can we use them for machine learning? It seems quite difficult. So, a high price to pay. And so, it's very open. Problem 3 is how do we deal with graphs that are highly non-Euclideans? We've talked about sampling densities, but we can also just talk about pooling layers, downsamplings. If you have a grid, it's very easy to unzoom an image. You just pack pixels in homogeneous bins of like 4 by 4 pixels, and in each of those bins you compute the average value and you're done. So that's for a grid. But what about a clique, for instance? A kind of very homogeneous graphs where everyone is connected to everyone. How are you going to decimate this kind of point cloud, this kind of graph? How are you going to decide that those points should be grouped together and those points not? Okay, on a grid, it's easy because you have this 2D structure, points are far away from each other. On a tree, it would also be easy, but on a highly connected graph, it's not. So then you have to make a choice, and every time you make this choice, you wonder if you're destroying all the important structure. Also, you know that whenever you define convolutional neural networks, you have this idea that you have a receptive field, that the value at any given pixel is a function of the initial pixel values, in a kind of cone of light that is a function of your sampling layers and the size of your convolution filters. But at least you have this intuition that information flows between the different pixel values. But how is information going to flow on this kind of graph, where you have 2 clicks and a bottleneck? If we're dealing geometric deep learning on this kind of structure, does it mean that every time I want to send information from this place, from the left-hand cluster to the right-hand cluster, everything is going to be squashed in a single feature vector that's going to travel with the convolution? Immediately you see that problems can happen. Problem 4, maybe a lower level issue, but which is probably actually one of the most important ones, is that all of this deep learning stuff is done on GPUs. Okay, hardware, massively parallel hardware, which is super optimized to handle textures, do contiguous memory accesses, these kind of things. And so on GPUs, and we're going to talk about it in detail in the last lecture of the class, it's easy to implement convolutions on grids, because with convolutions on grids, we have fixed and continuous neighborhoods. Okay. What do I mean? You know that an image is stored as an array, as a contiguous array of numbers, and the standard convention, the C convention, is to say that they are arranged row-wise. Okay, so you have pixel 0, 1, 2, 3, blah, 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 blah. Just exactly as when you read text. Now, what kind of information do I need to compute the convolution value for this pixel? You need, your compute kernel, like your compute unit, your GPU core, needs to have access to the pixel value in this square neighborhood. And loading those memory values is going to be fairly easy, because those are just 5 contiguous chunks in memory, 5 contiguous chunks of size 5, okay, that you can load in parallel. So the thing is that our code, everything we write in Python actually calls C++ code that has been compiled into binary code. And compilation is a huge topic, very complex and very important, that deals with all the optimization you can make ahead of time if you know what you're going to do. And here, maybe you understand that it's going to be possible to compile, to optimize heavily the compilation of convolution kernels. Because my code is going to know that I just need to make exactly 5 memory accesses at 5 different memory addresses that I know ahead of time. There is a constant offset between them. So it's going to go blastingly fast. But now, what about graphs? Okay, here I don't have an image. I have a graph with 1, 2, 3, 4, 5, 6 nodes, and varying degrees for those nodes. Like, for instance, this node has degree 3. This node has degree 2. Now, what do I need? What kind of information do I need to fetch if I want to compute a graph convolution on this graph? Well, for instance, if I want to compute the convolution value at node 1, I need to fetch the information about node 2 I need to fetch the feature vectors for node 2, 4, 6, aggregate them in a kind of contiguous neighborhoods, and then call a summation routine to perform my sum. So here, just to compute this one node value, I have been required to make 4 memory accesses at addresses that I did not know ahead of time, because this is not a fixed image. Basically, the addresses at which I had to make the memory accesses were given to me with my graph, as edges. And then I had to make a sum of 4 terms, but maybe for other nodes, I would need to do the same thing, but for 3 terms. For instance, for node 2, that only has 2 neighbors, so 2 neighbors plus itself, you need to make a summation with 3 terms. Okay, and maybe this seems like a detail. Okay, because if you do abstract big O of n, big O of n squared complexity analysis, those kind of problems do not appear. But if you try to actually make code that runs fast, this is a deal breaker. Okay?
Could you not rearrange it in memory prior to training or something, like upon the first compilation?
So what do you mean? So definitely, especially if you're dealing with point cloud, for instance, sorting the points so that points that are somewhat close to each other in 3D space are close to each other in memory is a big deal. Like, again, we're going to talk about it in the last session. So it's a trick that you can use, and that's going to work well for 1D data, 2D data, 3D data. But the problem with more high-dimensional data, just high-dimensional point cloud, is that it's not going to be that easy anymore. Like, because as we've seen, basically, if your data is not super clustered, those kind of tricks are not going to work. And for graphs, you cannot really do that. Like, or you can try to do that, but it's very complex, because at least if you try to handle general graph, then you never know. All kind of neighborhood structures could happen. And definitely, you're never going to end up with something as clean as this. So maybe a way around would be to try to do some kind of zero padding, etc. But then you waste a lot of memory. So I mean, trying to accelerate convolutions on graphs is a massive research topic. So people come up with ideas, but you see that it's very challenging to try to make something clever and that works out of the box in many settings. So yeah, there was another question. Oh, okay. So just to tell you that a lot of things that we take for granted on grids stop being true on graphs. And finally, maybe the biggest problem is that, as we've seen last week, saying that we have a graph is not saying much. Okay. Everyone has a graph. So the kind of ethos of geometric deep learning, which is to extend what we do on grid images, natural images, to graphs, is maybe a bit too ambitious. Okay, we're trying to develop methods that should be able to work both with molecule graphs, LiDAR scans of outdoor scenes, like, okay, this is a street in San Francisco, and social networks. Metric spaces that have very different properties, and where you have very different trade-offs. If you're working with molecular graphs, then maybe, okay, this is not a problem anymore. If your graphs are small, you can vectorize things. But if you're working with social networks with millions or billions of samples, they do not fit all on the same device. So you have to deal with cloud computing issues. It becomes a mess. So and we cannot combine everything at once. So it means that every researcher is focusing on an aspect which matters to his data, his or her data. And so basically, it's hard to really share insights between those different application fields. So, okay, all this community is very fast growing. Okay, in 2017, when people started to call this kind of research geometric deep learning, the whole field was a solution in search of a problem. People knew there were challenges, but were optimistic that they would be able to solve them. And so with an appealing pitch, the whole field attracted many people. You had computer scientists who were looking for new ways of defining convolution, new ways of combining features. Like, all this stuff is very exciting if you're doing computer science. Then you have mathematicians, maybe trying to look for new ways of applying their insights about random graphs, hyperbolic surfaces, these kind of things. And finally, most importantly, you have domain experts in many different fields looking for a breakthrough on their data, because everyone has a graph somewhere. And so everyone thought, okay, maybe this is going to change my life. And okay, all of this created many good things. Like you have a blooming corpus of methods. So if I had to summarize the literature since 2017, first you have dozens of different convolution operators that are suited to different settings, like some best for molecules, best for 3D point clouds, best for general graphs. We have renewed interest in theoretical graph machine learning. Like if you've seen the list of projects, you have lots of interesting ideas, of interesting questions popping up. Like for instance, what are the different types of graphs that can be distinguished or not using a graph convolutional neural networks, those kind of things. On the software side, you have several very useful extensions for PyTorch, like new binaries provided that try to speed up convolutions on graphs and all related things, like PyTorch geometric that we're going to see in the lab session, the deep graph library, Cheops, that we're going to talk about in the last session. You also have some hardware manufacturers trying to come up with connection machines or connection chips. Okay, it's an old dream. In the 1980s, people were also trying to design hardware that would be suited to graph neural networks more than GPUs. But the problem is that, as we're going to see in the last in the last lecture, hardware design is very hard. It's extremely capital intensive. Like, you know, a factory costs billions of dollars. And so is it going to get over the cliff? Frankly, it's very complex. It's very complicated. The good thing about everything we do in standard deep learning is that we're using graphics hardware. And the video game industry and the movie industry are so huge that essentially they carry the field on their shoulders. And even then, you know, with the current situation in Taiwan, maybe it's not going to be enough for the next decade. So for graph neural networks, it's an interesting but still niche field. It's very hard to justify the expense of designing custom-made hardware. Okay, so that's, I think, so good on the software. On the hardware, we'll see. And maybe most interestingly, I think, this whole idea that everyone has a graph, we should try to do data science with this graph data, has led to interesting cross-pollination between different fields. And I think it's one of the best things you can bring as a theorist, as someone who designs models, you know, who doesn't get into data, just to bring people together in the same workshop, let people understand that they all have the same problem, they want to say the same things. It's how you make progress. And so with this geometric deep learning community, it brought together people from computer graphics, from signal processing, from chemistry, and other fields. So that's good. But unfortunately, you know, in the context of a lecture, of a 2 hours lecture, it's very hard to recommend some methods over the others. Like, there's a clear lack of consensus. First, because the applications are widely different from each other. Second, because, you know, people have just been doing that for a little bit more than 5 years. So most theoretical and experimental works are just proof of concepts. You know, you don't have that many actual deployed models that you could judge in the real world. And finally, big issue is that the benchmarks that we use in the field, they are highly unreliable. Like, it's very, very hard to take the papers we read at face value. So basically, without taking the time to reproduce everything, you cannot really judge. So why are those benchmarks so unreliable? You know, I think it's an important lesson, even if you don't do geometric deep learning, you know, whatever the field you're going to work in, it's important that you understand that, okay? So in popular culture, we like to think that science, it's done in a vacuum. You know, we have those images of Archimedes being so obsessed with his math, you know, completely in his own bubble, that even when Syracuse was being invaded by the Romans, he was just saying, hey, don't disturb my circles, and he got killed. You have those paintings about those great men, those great men, like Louis Pasteur, alone in the lab, understanding that, okay, blah, blah, vaccines against diseases, you know. Actually, this is a picture that we have in mind, that science is done by old, wise people in their lab, alone. But okay, in the real life, at least today, maybe back in the days, it was true, I wasn't there to see it. is that scientific literatures are shaped by structural incentives. Like if you go on Google Scholar and try to understand the research community, you have very different dynamics that correspond to very different ways in which researchers are evaluated and rated by their peers or by the system, by the administration. So maybe I can start with three systems that I know pretty well. First, you have like French mathematicians, like ENS and all that. French mathematicians, essentially the ethos in this community is that people are mostly judged by their peers on their top 3 deepest ideas ever. Okay, like this is what matters. When people talk about someone, they do not say, oh, he has published 10 papers this year. No one really cares. It's about, oh, he thought about that. Just like I told you the thing about Gromov last week, Mikhail Gromov, okay, he understood that graphs have negative curvature, like trees have negative curvature. It's one of the things that he really brought to the field, and people know him for that. So it's a system that promotes very long-term and original thought. It's common anecdote that Andrew Wiles, when he was proving the Fermat theorem, he was kind of working alone for years on this, while publishing small papers here and there, just not to get fired, just so that people knew that he was not completely jobless. But, it's a kind of dynamics that mathematicians want to promote in their community, and so. I mean, they're left alone by the administration, at least in France, to do that somewhat. And so, okay, this is how it works. So it has good sides. Maybe on the more questionable sides, it's also a system where you have zero incentives to do outreach and interdisciplinary research, because people don't care if you've made a small theorem that is applied to medicine. They just care about super deep. You must show that you're clever. So that's one thing. Then you have the ecosystem, the environment in which I currently work, which is INRIA, where essentially the way we are evaluated is that every 5 years, we should have made one meaningful contribution. So we're not fired if we don't do that, but it's the way you get career advancement and all that. So, and the good thing, what I like about INRIA is that they are very agnostic about what this meaningful contribution can be. It can be a theorem, can be a piece of software, can be a patent, can be participation in like a standardization consortium, like MP3, these kind of things, or maybe a societal breakthrough. Okay, they're happy as long as every 5 years you can say, I have done this, one meaningful piece of stuff. So, maybe I wouldn't recommend it if you want to do number theory, but at least I think for AI applied research, it's really a great place. And you have many professors at the MBA who took a job at INRIA because it's very comfortable, because you're given this time window of several years where people trust you, and then you should do anything. Then at the other end of the spectrum, you have how it works just across the streets, in hospitals, French medical PUPH or MCUPH, who must be doctors, they must also be teachers, and they must also be researchers. So they have 3 hats at the same time. Unfortunately, in this system, you are essentially ranked according to your PubMed index or something like that, basically your H index. And why? That's because you can read the newspapers, you see that the hospitals are crumbling, that we don't have enough people to take care of patients. And so hospitals, just purely on the care level, they would prefer if the doctors were taking care of their patients 24/7. So the way the system works to enable research in medicine is that you have the Department for Higher Education and Research that sends money to the hospitals to compensate them for the loss of working hours of their PUPH and CUPH for their medical researchers. So, and with this money, they are supposed to hire short-term like consultants, people who will do the job instead. So that's how it works. And obviously, it's completely an administrative grid, and the amount of money a lab is going to get is a linear combination of the number of papers published this year modulated by like the impact factor of the journal. So as you can understand, if you fall below or behind the profitability threshold for the hospital is going to put pressure on you to close the lab, and say, okay, you're not bringing me enough money. I cannot replace you. Stop doing research, or at least I won't give you new funds to do research and focus on care. And this is the environment that produces this super inflation of low quality papers that is obvious to you as soon as you try to read actual medical papers. So people, most of the time, I'd like to stress that the overwhelming majority of the actors in those kind of systems, they work in good faith. Okay, it's just that you have rules. The rules tell you that if you don't do that, you're out. And so you have natural selection. If you want to stay, you have to play the game. So that's for what I can see here. And then I think it's important to understand that most of the literature in deep learning, in geometric deep learning at least, is, it's mostly done in computer science labs in US and UK universities. So it's important to understand what is the context in which these papers are written. I think you have at least three layers, three layers of incentives. You have like universities, professors, and students. Then, okay, universities, that universities in the UK or in the US, they are not really funded by the states. It's not a public service. It's a for-profit organization or semi-for-profit organization. And so basically they have to try to climb up the Shanghai ranking. And the reason for that is not because the Shanghai ranking is super meaningful from a scientific perspective, but it's just because one foreign student, I say foreign because, for instance, in the UK, foreign students pay much more than a British student. One foreign student, if you can attract a foreign student in undergrad, you bring essentially $30 or $70K per year. So it's a big pot of money. And so if you want to maximize the profit of your university, if you want to keep it going, keep it running in the long term, you have to maximize the number of papers so that you are ranked high in this kind of, it's a bit like le classement de l'étudiant en France, so that you impress prospective students, and so you can raise your prices. So university, they put pressure on professors to maximize this number of papers. So kind of in between, you have professors who kind of have to maximize the hype. That's because most of them, at my age, personally, I'm civil servant, I'm never going to get fired. In the US, it doesn't work like that at all. Like people around 30, they are on very unstable tenure track contracts. I don't know if it's something that you know, but basically you're on a contract where you say that in 3 years or in 5 years, you're going to get evaluated by the administration and by your department. And if your numbers are not high enough, it's bye-bye. Okay, so and it's very real. Like I have a friend in the US East Coast, he just got fired last month. He has to sell his home, relocate, find elsewhere, another place to stay. Another thing is that research, and this is also true in France, is that more and more research is done through grants. Basically, instead of getting recurrent, permanent funding for our research, we have to apply. We have to write like a 10 or 30 pages document where we say, I'm going to do geometric deep learning to solve AI or something. You get money for that. And then, for instance, the EU or the funding agency in 5 years is going to come back and to ask you precise receipts of every time you spend the money. And if you have not spent the money for the research that you promised, you're going to get in trouble. So, the way when we talk about grants, we talk about a system in which you cannot readjust your research that easily. You commit for 5 years to something. Okay, and maybe also people have started to grow. So all of these systems means that lately as professors or as senior researchers, at least in those countries, you are allowed to take risks, but you're not allowed to fail. Okay, if you fail, you're out. So obviously, it's a bit of a mitigated thing. And then finally, you have students who are the people who actually write papers. Like the overwhelming majority of papers in deep learning are written by PhD students who mostly try to target a job in the tech companies. Maybe that's your case. Mostly because you have many reasons, but simple reason is that they have significant debt to pay back. Maybe they live in countries where you don't have such a good safety net, a social safety net. And so on the financial side, the safest route is to do incremental research. Just claim state of the art every 6 months, publish at NeurIPS, CCML, ICML every 6 months. You're going to get your papers, you're going to get your job, you're going to be safe. That's really the way it works in most of these labs. And I think it's important that that I take this time to explain this to you, because it was not at all obvious to me when I was in France, normal élève normalien, blah blah blah, where we are raised in this environment where we are very safe on the financial side, and so we are encouraged to take risks. I grew up in the environment where people told me, no, you should have one deep idea. This is what you should do. Okay, the calculation is completely different for most people in our communities. So, and once again, I'm really not putting blame on people. It's just the way the system is designed. And once you see that, you understand many things about the literature, many strange things that do not make sense for you coming from French mathematics. So all of this means that you should take peer-reviewed papers with a pinch of salt. It's not scientific truth. So in the current machine learning community, you have relatively few actors who are incentivized first to review papers carefully. Like review it just, oh my God, you get emails, you try to do it as fast as possible. Personally, I feel bad for the authors, so I try to spend time. But, you're crumbling against under requests. You have very little incentive to document baseline thoroughly. Maybe you're going to find one baseline just to say that you have compared against a baseline, but you're not really interested in finding if the baseline works. You're interested in finding that your method is better. You have very little incentive to admit that your idea doesn't really work, because if you say that, well, what are you going to do with the remainder of your grants? How you're going to get published? You're not incentivized to make your experiments truly reproducible. So a very good thing about the machine learning community is that there is this peer pressure to at least put the code on GitHub. That's very good. It's, I think there are lots of good things about this community. And this is probably, I think, their main selling point, that there is this open source software culture, which is great. But this is nowhere near enough to make experiments truly reproducible. If you have experience in the field, you realize that making sure that people are actually able to run your papers 5 years down the line takes a massive amount of work. Basically, you need to make a library out of it. And that's because our software stack, the thing that we use, PyTorch, CUDA, the NVIDIA drivers, it's a software stack that breaks every 6 months. Maybe so far you haven't seen it, but oh my God, if you do your PhD, you're going to see that every time the NVIDIA drivers makes an update, it doesn't work. So you have to spend 2 days just finding what doesn't work. Every year also, you have PyTorch, they make a breaking change in the API. So sometimes the code breaks and you're happy. Sometimes they change the behavior. They basically just one line in the release notes, but they change the convention. Like this argument, before it meant transpose this way, now it means transpose this way. So it changed the results, but not the shapes of the arrays. So it means that everything becomes false out of nowhere. So it's very time consuming. And that's because it's a fast moving field. It's kind of, it's what happens when you live on the frontier, But just means that it takes time and we are not incentivized to do it. At Unreliable we are, but most of the places not really. So it means that this stamp, NeurIPS, ICML, it means quite little. It just means that people thought that this was interesting. That's about it. So you cannot really trust the conclusion of a paper without reproducing the experiments or checking the proofs carefully, or looking that 1,000 people have been able to reproduce the experiments. Okay, so that's why you have such trends in the field, is that in a context where it's so hard to build trust, you rely on word of mouth. So all of that to tell you that you're going to read many papers with impressive tables of numbers. And I think you should really take them with a big pinch of salt. So first reason is that some common benchmarks, they are just sanity checks. Like people who publish them or who package them in 2020, they say it's a sanity check. And then many people use them as real benchmarks when it's completely like it makes no sense. So let's look at MNIST, for instance. You know those images that I showed you 30 minutes ago. You have the original MNIST, which is was published like more than 20 years ago. It's in a context where things were much more difficult. And in a context where basically it's about mostly postal codes, so you target an extremely low error rate. Okay, the idea is how can I design a system which is going to be extremely reliable, so like 99.9 accuracy. Otherwise, it's not very useful. You have something that sends a letter the wrong way 1 time out of 10, it's a big problem. Okay, but so that's a real MNIST. And then people in the geometric deep learning community, they decided that since everyone knew MNIST, we should design our own graph MNIST, And maybe instead of making the effort of finding something that could be equivalent to MNIST but makes sense from a graph perspective, maybe, in chemistry, I think you have data sets like that. They just said that they were going to take MNIST and turn it into a graph. So compute subpixels, endow them with like a value, and then compute the k-nearest neighbor graph. And then out of nowhere, you have benchmark for free that everyone understands. It's just, can you, given this graph, classify it as a 9 or classify this graph as a 5? And when you look at the papers, you kind of see improvement over the years. You see that, okay, those are different models like vanilla graph convolutional neural network, MONET, gated graph convolutional neural networks, all of those models. You have a number of parameters that people try to stay constant, in benchmark. Like we really try to do the best we can. I include myself in the shaky benchmark community, unfortunately. So maybe we say, okay, 100,000 benchmarks, and then you have accuracy scores. And okay, maybe the vanilla graph convolutional neural network was giving us 90% accuracy, but then MONET 90.8, and then some neural networks, great, 97% accuracy. And people look at that, we print the numbers in red, in boldface, and we say, we've made progress. And then you think about it, and you say, but what does that even mean? Because if you look at the webpage of Yann Lequin, or you try to implement it yourself, you try to implement the baseline, but you go on Yann Lequin's website about MNIST, you have a table of all the standard baselines. And you see that the simplest k-nearest neighbor method that you could design on MNIST is going to have 95% accuracy, just with like 1 neighbor, 3 neighbors. And then if you increase the number of neighbors and you do super minor preprocessing, you get to 99% accuracy. Okay, and with a modern GPU, obviously you need 0 training to do k-nearest neighbor classification, and just testing on the 10,000 MNIST images, it takes less than 1 second. So you cannot even say that KNN is expensive. No, it's dirt cheap. So what does it's a real problem where you have communities that justify their work on toy benchmarks that are derived from data sets that are way too easy, and in which actually the target is to get from 99 to 99.9% accuracy. It's not to get from 90 to 96%. So, I mean, toy benchmarks are fine, but I think that if you want to convince other people that you are not just designing a solution in search of a problem, but actually solving a problem, someone needs to make the effort of designing real benchmarks. Then you have another problem, is that some common benchmarks have been saturated for years. Okay, this is kind of a new, very large-scale benchmark, ScanNet 200, where maybe you're not yet used to what those images are. Those are 3D scans of essentially an apartment. So you have like 2 beds, a sofa, these kind of things. It's common type of task in computer vision. Taking those 3D point clouds as inputs and labeling every point as belonging to a sofa, belonging to a pillow, belonging to a bed. And basically the standard benchmark, you only have like 20 classes. And people in the field, like researchers, they think, no, it's not enough. We've clearly fitted our models as far as we could, given the noise in the input annotation. And so we should go beyond that. We should extend this with 200 classes, keep our benchmarks challenging, because this is what benchmarks are for. But unfortunately, the review system pushes authors not towards using those, because this takes time. Maybe it means that if you pick a new data set, it means that you need to rerun all the baselines on this new data set. Whereas if you use the old data set from 5 years ago, making a comparison is very easy. You just copy paste the numbers from the papers, you trust them, you add your own numbers, which is 1% better, and you claim state of the art, and you get published. Okay? So as a researcher, you really feel this pressure towards not wasting your time challenging yourself, but just overfitting on a classic data set. And finally, those two examples, fine. I think this one is really is very problematic. In that some benchmarks have been taken out of context. Like some benchmarks have been designed very carefully, and then people semi-deliberately have not read the documentation. So this is a data set. I don't know if you've ever seen that. If you've done 3D geometry, probably. It's called the MPI, like Max Planck Institute, Faust dataset. So it's a dataset about human pose estimation. Okay, human pose estimation is a big problem in all kinds of fields. First of which, like automated driving, automated cars. Because if you want to have a car that runs not just on highways but also in the streets of Paris, you need to understand what on earth people are doing on the streets. Okay, this is the most challenging problem actually. So a question is, okay, you're given a dirty 3D point cloud. Maybe you just see one face of the model, maybe you have occlusions. And on this dirty 3D point cloud, you try to register to fit a reference template, mesh, okay, something like that. Because if you're able to do that, then it means that you have identified that this is a right arm, this is a left arm, this is a nose, etc. And basically, you have turned this dirty 3D point cloud into a high-quality mesh representation on which you can make simple analysis. Like, okay, because you know that this vertex is known ambiguously, then you're able to track the hands, you're able to say that he's doing that, all that. All these problems. So I mean, it's a task of interest, but how do you generate ground truth for this kind of problem? Well, the people in the Max Planck Institute, they did it. Essentially, they hired 10 models, and then they actually block printed kind of QR codes on their skins in blue and red, so to get like a super uniform, like to know that this point is this point, etc. And then they put them without their clothes, and they took photos from all around, and they were able to generate for those 10 people with 30 poses each, so around 300 real-life scans. They were able to generate a high-resolution 3D point cloud, and most importantly, ground truth meshes. Okay, like ground truth correspondence for those people with a mesh that has like 6,890 vertices. So that's very reference data set in the field. And if you go on the website, they tell you that the selling points of their data set is that it's hard because you have different topologies. You have missing data, like for instance here, you do not see the toes of the people, and sometimes you cannot see some places. And also you have self-contacts. And in human body pose registration, this is actually one of the biggest problems. Like it's easy to register this on this, this on this, but what do you do if people do that or if people do that? If people cross their arms, this is way more difficult. And everyone who works in the field knows that this is where the challenge really is. Okay. So, but to enable training and evaluation, they said, okay, we give you the 300 real-life scans, like the point clouds, we give them to you, and as ground truth, data, we are giving to you 100 meshes, like 10 poses for each of the 10 subjects, with identical topology. And we keep the remaining 200 scans. And the way the challenge works, or the way the challenge has worked for the last 8 years, is that if you think that your method is good, you upload your predictions for the positions of the mesh vertices on the remaining 200 poses, or subset of the remaining 200 poses. That's how it works. Very interesting benchmark. I mean, they really made a great job at it. And you have people, tackling this benchmark in real life, trying to solve it. But then what happened is that authors in the community on graph neural networks, and like even now, like it's even packaged this way in standard libraries, like the PyTorch geometric libraries, have decided to create a kind of fake benchmark out of this real benchmark. And the way it's done is that first, authors in the graph neural network community, they don't want to deal with point clouds. Okay, with dirty point clouds, it's not a good fit for their method. So first, you start by discarding all the original point clouds with 300 scans, and we focus entirely on the 100 pre-aligned meshes. So essentially, we throw away all the real data and we keep the annotation labels. And then we define a new problem, which is, okay, given those graphs, like those 100 graphs, I assume that for every graph, I have a three-dimensional feature vector, like x, y, z coordinates. So I have everything I need to define a convolutional neural networks. Convolutional neural networks that works on the surface mesh. Like all those surface meshes, they have exactly the same triangulation with input features, and people try to define graph convolutional neural networks on those meshes that take as input the XYZ coordinates and output the index of the node. Like, is it the node number 1? Is it the node number 2 or the node number 6890? Okay. And the way the new benchmark is designed is that we train on 80 surfaces and we test on the remaining 20. And the thing is that, okay, maybe it's a cool benchmark for graph neural networks. Try to see if your model is expressive enough, like can it learn these kind of things? Even though there is kind of a strong suspicion that those models, they're just overfitting on the precise triangulation. Because, if you're given those meshes, maybe you do not even need the XYZ coordinates to know that this is a nose, this is a toe, etc. Because maybe you could see that just by looking at the triangulation pattern, because you know that the only node that has 10 neighbors is actually the tip of the nose, these kind of things. So there is suspicion to that. But most importantly, this problem is completely irrelevant to shape registration, to the original problem. Because the whole point of shape registration is that we do not have this ground truth data, and that it's very expensive. It's ridiculously expensive to get this ground truth data. You need to block print things on the people's body. The whole problem is, how do I get this clean representation out of a dirty 3D point cloud? And basically, authors in the graph neural networks community, they semi-deliberately forget about that. And then basically they are able to solve this problem because it's not that hard, and then claim, then with graph convolutional neural networks, you solve 3D shape registration because you're able to show human body poses, errors, etc. And so it's, and I think for most people, it's completely done in good faith, because to understand that there is a problem, you need to do more than just download the PyTorch geometric package and download the prepackaged dataset. You need to actually look at the Faust dataset, realize that, that you have so many information that was not given to me. You try to understand why it's so, and then you read everything and you understand that this is what happened. But most people, completely in good faith, do not really ask themselves the questions, because most of the time in the graph convolutional neural network community, maybe people are not that interested in 3D data. They're interested in graphs, so they write papers about graphs. And then last week, before the NeurIPS deadline, they say, oh, I need benchmarks. And so they download something that looks cool, that's going to generate nice figures. They run the thing, they see that, okay, you have already a dozen authors who did that, so I can do it too. And that's how it works. Okay. So, okay, all of that to say that it's very hard to judge if you're not an expert in the field. So what I would advise you is that, first always try to keep track of both classical and learning-based baselines in each application domain. Do not just hang around at NeurIPS ICML. Usually for any applied subject, you also have a dedicated conference, dedicated journals. It's important to read those, okay? Because definitely the people who work in a pure AI community do not read the actual baselines. And at the end of the day, I don't think I'm here to develop methods that are going to impress other AI researchers. I'm trying to solve actual problems in the hospital. So the thing that this is time consuming, and it's very hard to understand like 4 or 5 different application domains. I think if you focus on 2, 3 subjects at most, it's already very good. It's very hard to keep track of community. So all of that, in this context, lately we've seen that there is currently a wave of papers in geometric deep learning. It's very likely that it's going to fade in most application settings and stick in some very productive niches. Like shape analysis, I think it's certain that it's useful in shape analysis. Chemistry, very likely. Social sciences, I don't know. And this is how scientific progress takes place. Okay, this hype cycle, it's very normal and a well-documented phenomenon. So maybe it looks like very harsh criticism, what I told you. It's just something that everyone knows in the community, but that we do not talk about in lectures. I think it's important, just to let you know about it and maybe take it less dramatically than it would if you were a bit too naive and arrived in a research lab and discovered that. I mean, I saw many people who were a bit heartbroken after this reality. Basically, my impression, so I'm going to talk at the end of the lecture on the influence of big tech companies, because they have massive cultural impact in our communities. So that's one thing. I think my impression from journal and conferences is that they are really trying to do their best. Especially the people who handle like the Journal of Machine Learning Research, or the people who handle like the NeurIPS ICML conference, you can see that they try. I wouldn't say the same thing about CVPR, for instance. Like CVPR, I had very bad experience with them. Like the remote CVPR I did, like it was 2020. They did not even sort the papers by topics, just alphabetical orders. They gave us random times. So, I passed at like 4 a.m. So, I think it's a sign of a community that doesn't care about people. But if you go to NeurIPS ICML, it's not at all the same thing. Like at NeurIPS, like during COVID, they were making their best effort to provide like a UMAP visualization of all the papers at this year's conference. It was interactive, so you could see your paper, you could see your neighbors, you could bookmark them. I know many people who do reviews for like JMLR or NeurIPS. I mean, you do what you can, but the thing about this community is that it exploded completely in a decade. So you have very few senior people. You have very few people who are way older than I am. Like, okay, I don't have that many. So they don't have time to manage all of this. And on top of that, like most of the young people do not stay in academia. It's kind of an exception rather than a rule to stay. So you have very little manpower, and so they have to do a little bit of herd management. That's the best you can do. Frankly, I put zero blame on them. Basically, I put zero blame on anyone, except maybe the people who design the US university system. Okay, this is something else. But apart from that, I think overwhelmingly people work in good faith, try to do their best, but it's very hard. Like you have complex issues. And so I think you have clear causal relation between the rules, the demographics of a community, and what is produced. And overall, I think all the thing at NeurIPS, ICML, you have lots of hype. Sometimes, come on, guys. But overall, it's relatively good quality, I think. Maybe it's a bit wasteful because it's nearly a whole generation of engineers doing that. And maybe people could disperse a little bit more, but it's pretty good. It's open source software. You know, you look at other scientific communities where everything is closed, people do not want to share. It can be way more toxic than it is in the ML community. You know, given the money involved, given the strategic issues, I think the last decade was done in very good spirits overall. So, but as I told you, it's very hard to select methods that really work and that we should teach. I'm sure that in 5-10 years, it's going to be easier to make a lecture on geometric deep learning, but currently, clearly it's not. So I said, okay, I'm going just to show you 2 projects that I worked on and try to give you some feedback on what I think about all that. So first project that I worked on, I was very lucky to work with people, especially at the you know, I was in a lab in London in close collaboration with people in Lausanne. You know, a real lab where they were doing protein design. So in a wet lab, and not a wet lab combined with a very good CS team, computer science team. So you know, I worked with like Pablo Gainza and mostly Ferrison, who's finishing his PhD now in Lausanne. You know, like super interesting interdisciplinary people in the lab of Bruno Correia. So I mean, very happy for this collaboration. And essentially the work was about doing protein science and most importantly docking, trying to understand the docking of proteins. Okay, I don't know what you know about biology. I do not know much. I just read some books, but that's it. And from a distance, you have at least 2 different types of problems in bioinformatics related to protein science. The first one is to understand folding, to understand how the DNA is coded into RNA, and then how the sequence of amino acids fold in 3D space. And that's important because basically getting 3D structure is very hard. Like, you know, my uncle has a lab about it in Zurich, can tell you that taking one of those pictures, typically it's 1 year of work, okay, or at least months of work. Whereas now we have excellent DNA sequencing tools. So we know much more about the sequences that we know than we know about the protein structures. So if we are able to fold those in 3D space, it would be great. Okay, and obviously, as I'm sure you know, there has been lots of progress made recently on these issues. And the converse problem is, given a target protein shape, like you know that, okay, my drug should have this shape so that it binds this way to the virus or something. Can you design a sequence of amino acids that will fold as you'd expect in 3D space? That's protein design. Mm-hmm. So that's one third. Then a big problem where obviously you have ties to language processing. You know, it's a bit like a text. And so interacting between sequence processing and 3D geometry. And then the other problem is purely 3D geometry. Like, given your 2 proteins, can you understand how they are going to bind together? How they are going to interact with each other? And at least as a first level of approximation, you can say that it's only a function of the surfaces, because like the inner structure determines the global shape, but then the atoms which are in the inside of the protein don't really interact with the outer world, except by providing like a structure to the protein. So you have this problem where, okay, maybe you have a data set of pairs of proteins interacting together. You'd like to understand why they match so well and why they do not match with the other proteins. So a physical prior that you could try to inject into a machine learning pipeline to do this is that we do not really need to deal with the full volumes, and that what we are really trying to do is to look at surface fingerprints, you know, try to understand what makes a surface patch so attractive to another protein. So that's why, you know, maybe a natural idea, if you come from this field, is to try to do deep learning on local geodesic patches of size around like a radius of 10 angstrom, so 1 nanometer. you have those geodesic patches, which is a typical size of a docking site. And on those patches, you compute geometric descriptors and chemical features, that describe what is below the surface. Is it like a carbon? Is it a nitrogen atom? And then given those 2D images, you try to learn interesting binding features. So the way it was done, in this proof of concept paper 2-3 years ago, was to try to apply geodesic convolutions or just convolutions on those geodesic patches. So the pre-processing was to take all the proteins at a very high level. You can think of this as a classification problem for geodesic surface patches, because you take your data set of proteins, which contains several thousand proteins, or maybe up to 200,000 proteins on the protein data bank. Each protein configuration equals 1 paper in biology, so massive amount of work. You take all the surfaces, you cut them into patches, and then you try to design a classification algorithm that can tell you that this patch is a good binding site for this other protein, and this patch is not going to interact. So you can kind of come back to 2D images from 3D structures. And this type of architecture, so you have a question of how do you orient the patches? So, related to the Unreliable theorem, you have this question, maybe you can try to do tricks to orient them, or you apply your pipelines in all different directions, and then you compute the maximum score. You do data augmentation, so you can try to find workarounds. But at the end of the day, you will end up with an architecture that has built-in invariance to 3D rotations, translation, and the inner content of the protein. Working with geodesic patches means that you're not influenced by what is inside, and you're not influenced by where the patch lies in 3D space. And that makes sense for physics, for physical reasons. Another good reason is that if you do that, you enforce a locality prior. Like you know that you're not going to overfit on scattered patterns. Like you're not going to hallucinate that a protein binds to another because you have a nitrogen on the other, which is far away from the docking site. Like we know that chemical interactions are local events on the protein, so they should only be influenced by local neighborhoods. So that's the idea, and we hope that once we have trained such a convolutional architecture on geodesic patches, then we should be able to understand why ligands dock inside protein pockets, try to make this kind of segmentation, basically this classification of geodesic patches, which is equivalent to a segmentation of protein surfaces, and also enable a fast kind of search engine for protein-protein interactions. Because you take 2 proteins, you apply your network, and you get a likelihood score of whether or not they are going to match. So that's the idea. Obviously, you need to be very careful about the way you construct your data set, otherwise you have data leakage. I don't understand this at all, but I trust my colleagues who are actual biologists to do it carefully. So, okay, this is a paper that was published like 3 years ago, and it was received extremely well, okay, by the community. It was on the cover of Nature Methods in like February 2020. But if we're honest, it was just a proof of concept. First, because it's very slow. This pipeline is extremely slow because you need to pay a lot of pre-processing to train your network. You need to turn your 3D point clouds into geodesic patches that you have to store. So in practice, terabytes of geodesic patches, and then you train the thing. So, I mean, it kind of works. I mean, once you've done the pre-processing, it's fast. You're just dealing with 2D images. But it's clearly not online. And so, for instance, with this type of pipeline, first, it's expensive. So it means that only big labs can afford it, like big labs in Switzerland. And also that you cannot really do protein design with this kind of things. You cannot update a protein and try to see if it's going to match, because we're going to have to wait like more than a minute, to to apply our network on a new possible protein. So that's when I joined this collaboration, and as you're going to see in the next, in the last session of the class, I've done a lot of work on speeding up geometric computations, and so we show that it's possible to do the same kind of things, geodesic patches, geodesic convolutions, not on 2D images, but directly on the point clouds. It's possible if you implement things well. To emulate geodesic convolutions on point clouds with oriented normals, and you get the same kind of model, but like 1,000 times faster, with no storage costs, fully differentiable, and so it's nice. Okay, so basically my part in all of this was to enable just extend the reproducibility of these results, and basically allow people to work with a single GPU and try to see what they could do. So that's one thing, but then you ask yourself, is it really a revolution? And if you look at the literature in protein science, honestly, then I don't think so. I wouldn't say so, because obviously structural biology, it's a huge field, massive amount of money, massive amount of public funding for it, and private funding also, because if you're able to do that, then the hope is that you're going to be able to design new drugs, and this is super important. So people, bioinformaticians and all that, and biologists have been working on docking software for 20 years. And if you look at the papers, the most famous one is the Rosetta software. If you look at the papers where they describe the Rosetta software, then de facto, if you had to write it today, you would say that it is a hybrid point neural network that combines physical potentials with data-driven residuals. Like the way this software works, at least the version that was published in 2017, is that it defines an energy function between two protein configurations. Basically, it takes as input 2 point clouds, and it computes a likelihood of matching for this precise configuration. And this energy, it's a sum of physical terms, like van der Waals interactions. So basically, the software 20 years ago, it was just the physical terms. Then they realized that, it doesn't work. So maybe we should add some kind of statistics. We should fit statistical models, like piecewise polynomial models, to fit the residuals to explain what happens. And in the modern version of the software, you have huge tables when they tell you that this residual has this affinity with this other residual. So in a way, people were already defining weights for point neural networks, but kind of by hand. And that was 5 years ago. And now they're using, in part, point neural network architectures. Okay, and then the way it works is that once you have an energy, then it's not that hard to sample different configurations and pick the ones that have the lowest energy. And those are your docking configurations. Okay, so just a picture to tell you that even if in the machine learning community, we like to say that deep learning revolutionized everything, I think you have to take a little step back and realize that people, especially in those fields, they're very clever. They have the same computers that we do. And so usually we end up converging on similar ideas. So my personal feedback on all that is that, what we did, okay, very well received by the community, but it's just a prototype. It just shows people how far you can go if we drop the complex physical terms, like the very advanced van der Waals potential. Like van der Waals is very easy to implement, but other terms are much more tricky. So we say, okay, we're going to drop that and just try to do learning with an architecture that preserves the symmetries of the problem. And this is what we call massive, demassive. And it's interesting as a data point, in the space of methods. See how you can go. Another thing is that, if you implement things well, with clever geometry and code, it's totally possible to do interesting science on a single GPU. Like you do not have to have a massive cluster to process those protein data sets. At the end of the day, it's like maybe 100,000 3D point clouds with a few thousand points. I mean, a PlayStation 5 can handle that very easily. I mean, we live in 2022, it's not 1990 anymore. Consumer hardware is already good enough to do very interesting research on this type of data set. Just that you have to implement things well. Third point is that, okay, I stress again that what we do, even though it was published in good papers, conferences and all that, it's nowhere near close to a finished product. Partly because, okay, it takes a lot of time to validate things on a wide range of applications and that. And also because the software stack breaks every 6 months, and maintaining software is a full-time job. So every 6 months, there's someone on GitHub telling us, hey, I downloaded this, it doesn't work, what happens? And I'm like, oh my God, I have lessons to prepare. It's very hard in an academic environment to do several things at once. And so the people who develop Rosetta, they have a massive lab dedicated just to this. As outsiders, we cannot do it. Okay, it's not even a competition. I think that as outsiders, you can just propose stimulating ideas and tools. You have to stay humble because we do not understand, or at least I do not understand the full context on all this. But I think that if it can maybe help the people who develop Rosetta and other software to use GPUs more efficiently, that's a big success. Yeah. So second problem that I worked on is shape registration, but not for human poses, but for lungs. Okay, I already showed you those images, I think in the first lesson. Those are pairs of point clouds. So here I have 4 pairs of point clouds that have been acquired using like 3D scan, where we can see the blood vessels in the lung at exhale and inhale time. So upper row, red, it's exhale time, so shrink. And bottom row in blue, it's inhale time. So we have those 2 semi-noisy 3-point clouds, and we'd like to register them together. We like to find a point-wise correspondence between points that exist. That should exist because it's the same person, just 3 seconds of interval. So it's not as though we are doing a registration between different subjects. Here, definitely there should be a correspondence. And it's pretty tricky. First, because we are dealing with very complex deformations. It's not at all linear. Second is that it's quite high resolution data. Here are the point clouds. It's 60,000 points each. Okay, and if you do less than that, you do not see the small vessels at all. So you need to target this type of scale to do interesting anatomy. It's not just undersampled plane or undersampled chair. It's those kind of shapes. You need points. And finally, the baseline is already very high. Like you have legacy software from 15 years ago that is able to register 2 3D volumes, those 2 kinds of 3D volumes to a very high accuracy, like less than 1 millimeter. The problem of those software is first that they're quite slow, so several minutes, and that since they rely on the volumes, on the full volumetric information, we don't know. I mean, it's very hard to be sure that the software is going to be robust with another medical imaging device. Like if I change the acquisition parameters, what's going to change? Maybe I'm going to change the local texture, the local contrast, and then maybe everything is going to fall apart. It's a massive problem with medical deep learning, medical image analysis, that the appearance, the texture of our medical images is not nearly as standard as it is with natural images. I think all the iPhones, smartphones, they take more or less the same type of pictures. Whereas if you look at an MRI made on this specific Siemens scanner at the Hôpital Cochin and another MRI scan done in another hospital with a different machine, they do not look exactly the same. Because basically those big machines, they are fine-tuned to the tastes of every individual radiologist by the technicians. And so if you have an algorithm that relies too much on this textual information, you have to be cautious. Okay, so basically the idea is that if we're able to solve the same problem but only using the geometry of the data, using only the point clouds, then for free, we're going to be very confident in a cross in the cross-platform abilities of our method. So that's why it's interesting. Basically, we try to solve a normal problem, but very fast and using sparser, sturdier data. So if you look at what people want to use now to solve this kind of problem, it's essentially point neural networks. So I don't know if you're taking the lectures on 3D point cloud analysis, of Tammy Brubaker, François Goulet. Very interesting class. You're going to see those type of methods, those type of architectures. So, here, basically, it looks like a unit. If you know what to look at. What I'm displaying is a diagram where, as input, we take the source and target point clouds. So n points, m points, different number of points, and 3-4 channels. 3-4 channels that correspond to x, y, z coordinates, and maybe the radius of the vessel. And then, basically, the network is going to compute a pyramid of features at different scales. So local descriptors and more deeper descriptors. So we assume that our networks, our point convolutions, are biased towards defining some kind of shape contexts that are going to flag where you have 2-3 branches. Maybe they understand the angles of the branches. That's the idea that we have in mind. I didn't inspect it carefully enough to tell you that this is for sure what's happening, but we think that's what happens. So you get like fine descriptors and coarse descriptors, and then in a coarse to fine fashion, we try to combine those descriptors to generate a 3D deformation field. And this is done in a kind of custom architecture that performs well for this kind of tasks, where in every block, you have a deformation field at a coarser scale. You have what the features look like at the current scale, and then you try to fit, like you warp the input point cloud onto the target, and you compute a kind of distance field that tells you, okay, here it's not perfect, maybe you should go a bit more to the right and all that. So you have this very custom architecture that incrementally fit residuals to the 3D vector fields and output you just 3D velocities, a kind of optical flow that should match two shapes together. Okay, so you can look, but it's very idiomatic in this community to use those kind of networks. And the thing is that if we try to use those architectures in practice, they are both good and bad news. So the first good news is that, okay, those architectures that compute descriptors at all scales, okay, we can train them on synthetic deformations. So to train them, we take our input point clouds, we generate smooth 3D velocity fields. So we generate deformed point clouds for which we know the precise point-wise correspondence, and then try to essentially solve the inverse problem. So reverse engineer this deformation with a network. And when you do that, well, you're going to see that the network is extremely good at pairing branches together. So clearly, it's not, those networks are very good at finding that this finger goes into this finger goes into this finger, which is something that is not easy to do using mathematical formulas. Like I tried. People have tried for 20 years. It's really complex. But on the other hand, it's nearly impossible to train this type of model to a very high accuracy. So in a way, it's a bit frustrating. You have a network that does the hard part very well, but which is nearly unable to do the final step. You clearly have diminishing returns in terms of model size of the training data set and all of that. And it makes sense because at the end of the day, those are just piecewise affine functions. If you fit this kind of model to your data, basically, if you fit piecewise affine models to a smooth curve, you need a lot of points to get it. So even if you capture the global trend, getting something that is appealing to the eye is going to be hard. And since we're in a context where the baselines exist and are very accurate, you have to do, you have to perform to those standards. So in practice, I think everyone who is pragmatic is going to realize that those methods have very complementary strengths and weaknesses compared with standard deterministic baselines. Because registering shapes that are close to each other is very easy using basic math, like optimal transport theory or these kind of things. So that's why I think that typical architecture that you would see in applied papers, and if you talk to people in the industry, they will also tell you that this is what they use, is architecture that first perform an affine pre-alignment, then apply your deep prediction network that you've trained on synthetic data and smooth a little bit the velocity fields, because we know that the breathing movement is not super sharp. So we apply this prior to ensure that we have plausible deformations. And then once you have done this centimeter, this registration up to a centimeter accuracy, you use some kind of optimal transport, smoothed post-processing, and you get something which is pixel perfect, which is our target. Okay, so those kind of pipelines are very easy to train on synthetic data. You can scale them up easily now, with our GPUs to 100,000 points in 1 second, and it gives you good results on benchmarks. But we're going to talk about the benchmarks. So first, just what does it look like in practice? Okay, so this is my input source point. This is my target. So small lung, large lung, I want to fit them together. If I fit them using just an affine registration, this is what I get. So from a distance, you say, okay, problem solved, but then you zoom in and you realize that, okay, it doesn't work. Okay, so clearly the breathing movement is not just an affine change of coordinates. So once you apply your point neural network and smooth the velocity field with something like a diffeomorphic model, this is the kind of result that you get. Something where, okay, clearly the problem is nearly solved, like the branches are paired together, and we've done the hard part, no questions about it. But getting pixel perfect accuracy, it's tantalizingly difficult. And so once you have this, then you think, okay, maybe I can use some kind of nearest neighbor projection. But if you do that, you generate some artifacts, which are strange. So maybe you try to do something a little bit more clever, like optimal transport, which is nearest neighbor projection with a constraint of incompressibility, so which makes sense here in this context. You get something that looks good, and you're fine. You say, okay, this is a nice prototype. So what about the evaluation? Well, first thing we could do is to evaluate it on a standard benchmark in this community, like at NeurIPS, the community about 3D point clouds, which is something related to automated cars, automated driving. So here I'm showing you one pair of point clouds from two different views. So this is a view from above. This is a front view, like the view that was actually taken by the camera. And we see that, okay, we have cars that are moving, 3 cars. We have signposts. And then we have points on the ground that typically, have been removed in the red frame, but that have not been correctly post-processed, pre-processed in the blue frame. Okay, and what we're trying to estimate is a kind of 3D optical flow between those point clouds. Try to see that, okay, like this car is moving to the right. This is those are fixed objects, these kind of things. So just to tell you that this data set, it's so 3D flow, it's derived from an original data set that comes as a set of 2D images plus depth estimation. So we can say, okay, is it a fake benchmark? I don't really know. Okay, because I'm not an expert in automated driving. So it's what people like to use, but maybe it's questionable. Maybe real people interested in cars, they work directly on the 2D plus depth estimation. It wouldn't surprise me, to be honest. But like you can see it maybe as an interesting toy problem where you have loads of different rigid body deformations. And then you have a table, because it's NeurIPS, you have to put a big table. And what can we see here? Okay, I'm showing you like 10 different methods You have deterministic methods like iterative closest point, coherent point drift, those kind of things. Maybe some self-supervised neural network. This is just a very simple baseline where you have optimal transport plus some kind of smoothing. Then you have here some point neural network like FlowNet 3D, PWCNet, FLOT, just papers in this community. And then the kind of thing that we did, okay, this hybrid pipeline that combines the point neural networks with optimal transport, like robust optimal transport. That's why we call it robot. And then you have several columns. First, they tell you at which resolution we are working. So most point neural networks are not very scalable because they are not implemented using the latest binary routines, the latest CUDA kernels. So you can only use them with 8,000 points, but other methods, like especially the thing that we did, can completely scale to 30,000 points. Then you have the time that it took to run the network on a pair of 3D frames. You see that you have times that we have, that's because we ran them, and then times that we don't know because we couldn't, like we already made so many experiments, we didn't have time to run yet on the baseline, and so like everyone else, we just copy-pasted the results. Then you have the memory footprint, so same story. And then you have many different performance metrics. First, you have like the typical average error. And then you have accuracies, accuracy percentages, because average error can be very influenced by outliers. So maybe instead you want to look what is a fraction of points that are mapped correctly up to a 5 centimeter radius. So that's ACK3DS. Then ACK3R, I think it's like 10 centimeter error. Outliers 3D, how many points are completely left or are basically not excellent. And then here EP2D, the same scores, but if we went back from our 3D scene flow estimation to a 2D optical flow. So big table of numbers, impressive and all that. But what I want to show you is that those numbers, they can be a bit misleading. Like when you see that, you do not see much except that, okay, our method is the best, please publish us with 95% accuracy. You have many more information to read if you know what to look for. And maybe for me, the most interesting fact about this table is not that our method that, okay, we train and blah, 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 performs well. This is expected. What wasn't expected, at least for me, big surprise, was that, okay, you look at all those neural networks paper from 2018, 2019, 2020, and they claim accuracies of something like 10 centimeters, maybe 20 centimeters. They registered maybe 40, 20% of the points. At least the first iterations were not very good. And what's surprising is that they are completely outperformed by very simple baselines, like optimal transport, implemented well. We're going to see maybe how it works in 2 weeks. Okay, but you see that with very simple geometric computations, without any training, with very small runtimes, you get a method which is very competitive with this deep learning literature. Okay, and I think it's something that is kind of typical. At least when I review papers for Mika and Urips and all, usually you see methods, you see the results, and you think, come on, if I took six months maybe, or 3 months to develop something using just pure math, probably it would perform just as well. Okay, and so sometimes it wouldn't. As I told you, I'm very impressed by what point neural networks can do on those lungs, etc. But sometimes it's not clear-cut, especially on this kind of data, which is actually a best-case scenario for optimal transport, if you know what optimal transport is. Yes.
Wouldn't we say that those first deep learning methods just had to pave the way, and that if there weren't there, you could not have developed some further models and so on to get better accuracy? And so that maybe at the beginning of applying deep learning to a field, you don't expect to reach the same performance as previous methods, but just to initiate the process so that people could have better results.
So I agree definitely that in some fields, like on graphs, in fields that are not super mature, it's totally like it's good way of thinking. Okay, maybe we start with what we know and then we apply. But this is not what happened with 3D point registration. This type of tasks has existed forever. You have papers from the 1970s where they are already trying to do that. Lots of methods have been developed. But the thing is that people forget, especially, because we go to a master's degree, we learn techniques. We do not really read what was published before that because we assume that everyone, basically you assume that your teachers are showing you state-of-the-art methods, things that work and all that. But then you forget that in academia, we have a huge novelty bias. And so in academia, we have to publish new methods to claim that science is advancing. And so we forget that people in the 1980s, people 20 years ago, they were just as clever, just as ambitious as we are today. They had to work with tighter computational budgets, but maybe it's a good thing. Maybe it means that their method was super, super fast now with today's method. And so I think that if you want to do credible science, you have to know about them and take them into account. Not because I'm claiming that optimal transport is going to work all the time. I really don't think so. Optimal transport has lots of pitfalls. But because if you only read papers published 2 years ago, then basically it's a very myopic way of looking at the literature in fields where so many people have worked and so many people have had good ideas. So that's the message I wanted to tell you. Another thing, okay, so if I had to make a recap on this registration project, well, the first personal feedback is that if we are pragmatic, if we want to actually solve a problem, I think it's very sensible to try to get the best of both data-driven and deterministic methods. In academia, we have a bias towards end-to-end models, where we say, no, I want to have a huge network that's going to solve the problem out of the box. But it may not be cost-effective. Second is that those table of numbers, they look impressive, but they can hide critical information. And second, about lots of criticism about our work. First is that the code base is not clean at all. Partly because when we were publishing this paper, most of the code was written by Shen Zhengyang, top PhD student in North Carolina. But me, I was actually applying for a position at INRIA, so I was super busy with that, and so I could not help him to clean the code. And so now, you go on the repository. I think it's reproducible, like you can press the button, it's going to work, but not much more than that. And so for me, it's a big regret. So top priority for 2023 is to develop a library of classic methods and also this as a cherry on the cake. But, I'm not going to claim that this is great code just because we didn't have time for it. Second is that, as I told you, the evaluation on the 3D scene flow is questionable. Shouldn't we work with the original today data? I don't know, because I'm not an expert in autonomous driving. And finally, maybe on something that I know much better, which is medical data. Well, the problem is that evaluating on medical data is very hard. We tried our best. So we teamed up with a lab in Harvard that gave us 1,000 pairs of images, 1,000 pairs of point clouds. We released them completely open source. And that's useful for training, to generate realistic examples, generate synthetic deformations. But we don't have the annotations because the annotations are super expensive. Paying someone, especially a radiologist, if you want to be credible, to annotate for every pair of point clouds, to annotate like 300 points and say this point corresponds to this one, this point corresponds to this one. It costs a lot of money, and we didn't have the money for that, so we only have access to 10 pairs with dense annotation for evaluation. So that's super questionable, and I'm sure that you can understand that. That's the reality of it. I think as academics, you try to find your niche. If you want to do super credible evaluation, it's a full-time job. And some people do that. It's fantastic. It's absolutely necessary. Me personally, I'm trying to bring the field forward in terms of geometry and in terms of computational routines. I spend crazy amount of time maintaining libraries and all that. I cannot do everything. Take everything I say with a pinch of salt. So now we see that. Okay, I think that's typical picture of what happens today with point neural networks and graph neural networks. Some people do more theory, as I'm sure you can say, looking at the projects. But then you see all of that and you say, okay, maybe it's a data-driven era. Maybe we should just learn our graphs. Drop this KNN structure, try to do everything data-driven. Why not? Okay, so maybe that's an excellent idea. Okay, so for instance, a very interesting paper is the one that presented dynamic graph convolutional neural networks. The idea is simple. What I told you so far is that if I'm given a shape, a point cloud of a 3D plane, and if I want to segment it, like I take as input the XYZ coordinates, I want to predict like an integer label that tells me those are the wings, those are the motors, these kind of things. Those are the wheels. Then I told you, okay, we should use a surface mesh. We should use a 3D connectivity structure. And then using this connectivity structure, I define a graph neural network. And then at every layer, I get features and I hope for the best. That's one way. But maybe what you could do is to say that since at every layer you have features, basically those are new coordinates for your points. And maybe it would make sense to use a k-nearest neighbor graph of this representation instead of the k-nearest neighbor graph of the first representation, the one with the XYZ coordinates. You can hope that if you do that, then instead of using geometric neighborhoods, you promote semantic neighborhoods. It makes sense. So very influential papers. I think for the chemistry problem, it doesn't make too much sense because for the binding problem, we know that it's actually local. We want to use this neighborhood structure, but for segmentation of parts, why not, frankly? Another idea could be to say that, okay, since we have UMAP, we have autoencoders, basically data-driven compression algorithms, maybe we should use the neighborhood structure of our data in a low-dimensional representation. Okay, that's one way of doing things. Another way is to say that maybe we should use transformers, like attention layers. I don't know if you've already seen that, if you're taking lectures on natural language processing. Okay, just what are those transformers? Well, those are techniques that initially come from natural language processing. Okay, the problem that we have is that we want to design language models that get a good representation of the meaning of sentences to enable, for instance, automatic translation, machine translation, so which is actually a great a great target. So you have this typical stereotypical sentence: the FBI is chasing a criminal on the run. And the way we handle this, not as strings of characters, because this is a bit hopeless. We handle every word as a token, so you can think of it as a node in a graph. And for every token, we have a vector of features. So initially, it's just going to be like an integer number, because we have a dictionary of all the words that we are likely to encounter. And maybe also a positional features that tells you that this is at the start of the sentence, this is at the end of the sentence. Okay. So you have this type of data, and you would like to define convolutional architecture that maybe predicts you at the end new integer labels that correspond to a translation of the same sentence. Maybe the same word, but in a different language, anything. So we'd like to do convolutions on those type of 1D sequences. The problem is that if you handle a sentence as a 1D sequence, if you try to use one-dimensional neighborhoods, then it's not super relevant. It's somehow relevant. But if you say that the word chasing should only interact with is A and maybe with FBI and criminal, then for instance, you're never going to see that chasing is kind of related to run, which is something that maybe you see on the feature vectors, like the features for chasing are close to run, but on the one-dimensional structure, you do not see it. So an idea is to say that maybe we should embed our feature vectors in a semantic space and perform the convolutions in this semantic space. So that's what I'm displaying here. Like every word corresponds to a token, to a node, and kind of displaying that the word is, like it's a verb, it's here. The word FBI is close to criminal because it's in the high dimensional space of semantic meanings. It's kind of related to crime. Chasing is related to run, so they are close. And so you hope that if you have a good embedding of your words or of your feature vectors, then you should be able to do convolutions in this space, kernel smoothing in this space, and let FBI interact with criminal and chasing interact with run. Okay, and what we call an attention layer is just that. It's a data-driven embedding plus a convolution in this space. And we call this attention because if you come back to the 1D text sentence, you have the feeling that chasing is paying attention to run and FBI is paying attention to criminal. But you could definitely present it just the way I showed you. And what we call a transformer is just a stack of attention layers, very well implemented, completely scalable, and people train them on fast. And okay, so that's for the basic intuition. In practice, the cheapest way of implementing this methodology while keeping a very expressive method is to do this, okay, to use those equations. So the idea is that for every point xi, you're going to compute what we call query and key vectors. So those are your embeddings. Okay, so maybe in this picture, I computed one embedding for each word, but if you want to enable asymmetric interactions, maybe you want to have different embeddings for like source signal and target signal, because with just one embedding per node, FBI acts on criminal the way criminal acts on FBI, and maybe you don't want that. So what we do, or what people do in natural language processing, is that you have a first embedding, which is called the QI, and a second embedding, which is called the KI, computed using different multi-layer perceptrons. Yes?
In that case, what would the convolution looks like?
Yes, so that's exactly the next thing. So you have, so those are your points in a high dimensional space of point clouds, and value vectors, which are just the values that you want to convolve. And then how do you perform a convolution in a space of point clouds? Well, actually, it's exactly what I presented to you in lecture 2 as kernel interpolation. Kernel interpolation, it's exactly convolutions with point clouds. And the cheapest way of making a convolution with high-dimensional point cloud is to use the Nadaraya-Watson interpolation, the one we saw where we were kind of computing barycentric combinations of our features with a super simple kernel, which is just exponential of the dot product between x and y. Okay, so if you remember those pictures, you had those input samples. So the circles here are the key vectors. The colors correspond to the value vectors. And the crosses correspond to the query vectors. So basically, with my key vectors and my values, using an Nadaraya-Watson interpolation, I define a function in high-dimensional space. And then I said that the new value, the new vector of features at position xi, corresponds to the value of this Nadaraya-Watson interpolation at a location which is that of the query vector. Okay, so you end up with this equation, which is what you find today in all natural language processing papers. And when you see that, you say, "Come on, guys, it's completely Hail Mary methodology. To hope for the best with multi-layer perceptrons. Completely, like it seems super simple, like all those sums of exponentials. But what people have showed that surprised essentially everyone is that this architecture, you can scale it. So okay, this is not that surprising because it's very simple, but it trains remarkably well on those web scale corpuses. Okay, and that's why so many people today study attention layers and transformers. So, okay, but what I wanted to show you, is that it relies on computational blocks that you already know. It's not a surprise because the hardware and the software, they have always evolved, co-evolved together. So Madariaga-Watson interpolation promoted the idea that we want to do kernels. People at school, they learn about those equations. And then when people doing natural language processing wanted to implement this idea, they came up with those equations that were easy to implement using like MATLAB, Python, PyTorch, because essentially the software was already there to do kernel interpolation. It's completely co-evolution of ideas. So that's why it's one of the main reasons why you have so much continuity in terms of algorithms, in terms of computational blocks, even if the way we describe what we do changes every decade. Okay, like you have huge trends in the way we name equations, but the equations themselves, they don't change that much. So, okay, that's super ambition. Basically, people see that and say, since I can do it on the corpus of like Wikipedia, the web, maybe I should do that for every problem. That's a very optimistic take on machine learning. And you have several problems. The first problem is that in most important settings, data is very expensive and data sets are fragmented. Okay, like the web or tasks that you can solve using the Amazon Mechanical Turk, like paying someone very cheap amount of money to annotate your data. It's more the exception than the rule for like interesting, impactful projects. We talked about protein structures. Every single point was months of work for a biologist. So even though it's public domain, even though people publish it, basically by pulling all the work that has been done in the field over the last 20 years, you have just 200,000 proteins. And with 200 proteins, it's not billions of texts, okay? So it's large enough to enable some kind of transformers, like it's good enough to enable that, but if you look, for instance, at AlphaFold, the papers, you have quite a lot of structure in the model to try to leverage a little bit of knowledge about the problem. Otherwise, it just doesn't work. Second is that we talk about medical images as if they were as simple to get as just taking a picture with a phone. But no. Like someone who's doing his radiology thesis, a great thesis, it's 50 patients. Okay, so like 6 months of work for a doctor, you document 50 patients because those people are real human beings. Like so first, it's expensive to note everything we have to know about them. And also you have lots of diseases that are quite rare, like maybe a few thousand people per year. So it's not at all the same scale. And finally, something like big business, clinical trials for drug, to test drugs and vaccines. One patient in a clinical trial costs a crazy amount of money. Like I think the average or median cost is something like $40,000 per patient. And in some settings like surgery, it can go up to $1 million, to recruit the patient, sign all the paperwork. Like everything around the clinical trial costs a crazy amount of money. And so in this context, which is super important, we've seen that with COVID, the game is not to say, give me 1 million patients, okay? It's how can I reduce the number of patients? We're working a lot to try to develop clever methods where to maybe cut in half the number of patients that are needed to prove that medicine is working, okay? You can just see that. Basically, do you prefer to come up with a model where there is 0 prior and you need 2,000 patients, or with a clever model where you only need 1,000 patients and you pocket the difference? So that's exactly the calculation that people are doing in this field. Finally, getting legal access to large data sets and computers is extremely difficult in any field, where you have significant societal impact. So like the big web companies, they benefit from their monopolies. Even then, it's not clear if in 20 years they won't have been broken up. But if you look, for instance, at medical data sets, society really doesn't want us to merge them together. It's very, very hard to have access to them. And even if you have access to them, it's very hard to have access to them with a good computer, because no one is ever going to let you download this data. You're going to have to work with the computers that are provided by the assurance maladie, you know, the national insurance. So it's not going to be a state-of-the-art GPUs. So that's the real world. Second is that bigger models, out of the box, they are slower, heavier, and cumbersome. And in practice, very often, you want to strike a balance between speed, accuracy, hardware and development costs, energy consumption. Both, you know, energy consumption is both for greenhouse effects, maybe a bit of greenwashing. The critical thing is battery life. This is a massive bottleneck, and this is one of the main incentives to develop low consumption algorithm. And finally, if you have an interpretable model, then you have a model which is easy to debug and easy to maintain. And if you're an academic, if you're someone in academia, you just want to publish a paper and be done with it. If you're in the industry, you have to plan for your future. What's going to happen to your model if it breaks in 10 years and that we are not paying you your handsome salary anymore? You know, instead we're relying on just software developers who know how to maintain it. This is a massive question. And so the thing you should have in mind is that super complex mathematical models are a bit like super complex transformer models. You have tons of parameters, tons of equations. People are afraid of that, rightfully so. And so they're only worth the trouble if there is no other option. So visibly, natural language processing, there is no other option. So that's what we study. But for lots of other problems, you have lots of competitors. And if you're not able to show groundbreaking advancements, that people are going to stick with a cheap, well-understood baseline. Finally, in mature fields, in fields where people know a bit about the problem, structure, it's key to generalize. Okay, this is especially true in fields that are close to physics and robotics. You know, in physics, we know a lot of things about the laws of nature. For instance, we know that, okay, if you shoot a cannonball, it's going to fall according to a parabola, up to frictions and all that. And of course, you can say that a parabola, you can fit that with piecewise linear functions. And maybe it's going to work if you're purely doing interpolation. But as soon as you're going to try to extrapolate outside of your training sample to do prediction, it's going to be very limiting. So instead, you know, that's why I presented to you the things about geometric deep learning. Maybe what you want to do is define an architecture that is trainable, but that still has a kind of correct computational structure, because we think that it's going to be essential to enable generalization outside of the training data set. So what you should take away from all of this is that we really have a continuous spectrum of scientific fields. I think in the MVA here, we're not doing AI. AI, it's not one big blob and we're all working together. It's more like it's a community of people who exchange ideas. And that's great, that's very important. It's fantastic that people from so many different backgrounds talk together. But it should not hide the fact that we are working on different problems. And very quickly, if you want to be competitive, if you want to have things that work, you need to specialize a little bit. So if I had to make a simple 2D diagram of archetypal domains, I think two interesting axes are how much data we have available and how much mathematical structure you can reasonably expect. So maybe astrophysics, it's a typical field where you have lots of mathematics. We've known that since the days of Galileo and Newton. And not that much data. Like the Paris Observatory is just across the corner. Super great, guys. I went there. Like you have one instrument, like you have lots of images, but in the grand scheme of things, it's not that much. So we expect that you need to do a lot of math, a lot of physics to understand the world, the stars. Then you have chemistry, you know. Then you have topics where you don't have lots of data, you don't have lots of math, like history, maybe economy. Those are the fields that we do not study in the MVA because we personally have nothing interesting to say about them, but those are obviously very important. And then you have the fields that you've heard about recently, like the field where we have lots of data. I'm thinking about situations in which you have simulators, like board games or video games, or web-based problems, like the processing of natural images, of YouTube videos, or of natural language. Those are also interesting, but you see completely at the other end of the spectrum. And if I look at a field that I know well, imaging science, you have different subfields within this umbrella term that correspond to different degrees of data availability and inner structure. I would say that working with natural images, I would not expect math to play any role. It's already a bit of a miracle that it is somehow relevant to study math, to study natural images. But if you look at medical images, much more standardized, you have no occlusions, less data, you can hope to bring something as a mathematician. And even more if you look at biology images, because usually biomedical images are much more rare. Like if you look at state-of-the-art imaging devices, maybe they're only available in 10 labs worldwide. So you need to define kind of custom methods. And so usually I think the more purely mathematical methods are more relevant in those settings than in those ones. Okay? So you have this spectrum. And this is what explains that you have so many different takes on what math and AI can bring to our society. On one hand, you have physicists who talk about the unreasonable effectiveness of mathematics in the natural sciences. It is a miracle that if you know about calculus, you're able to understand lots of physics. That's crazy, but it's true. On the other end of the spectrum, you have people who work with natural images, natural language, who talk about the bitter lesson of AI. The bitter lesson that people try to develop semi-mathematical model, and every time it's in vain because once you have 10 times more data, it becomes obsolete. Both are true. It's just that those are different fields. Personally, I'm really amazed that people try to do math for natural language. It's very courageous on their part. Then you look at that, and what I would like you to see is that maybe, especially in the media over the last 5 years, there's been a bit too much emphasis on those problems. People have talked about Go, video games, natural image, natural language, as if it was the only interesting problems for our society, as if AI was all about that. But those are interesting problems and very important problems, obviously. But the other things is important too. I think you try to fit in the niche that you like. Personally, I really enjoy working on medical images because it's a bit in between. I can choose. It's very much a continuum. So also you have this thing that big monopolies in every field, they will always claim that bigger is better. They will say that, okay, my rocket travels at 30,000 kilometers per hour. Your stupid bike only goes at 30 kilometers per hour. And maybe you see that and say, okay, maybe I should work on private jets. But you're wise enough to know that those raw performance metrics, they do not tell the whole story. If you have models that are cheaper, it means that they are going to be adopted much more quickly and have as big of an impact. And that's why I spend so much time talking to you about UMAP. UMAP for me, it's really a golden example of what people can do by just a simple model, a simple Python library, and so impactful. So basically the picture is trying to choose your own path. I have taught mathematics for a decade now, and I've always been surprised by how different we are from each other. I think your mind is not the same as mine, clearly not. I'm trying to provide you with a geometric perspective on the field because this is what I understand best. I'm sure that you have other ideas. Sometimes you want to criticize, and that's great. And so try to find something that you really love and not always gravitate around the same handful of jobs and positions. I say that because I'm sure that you've heard about Google, Facebook, all those companies, and over the last decade they have had a very deliberate marketing strategy to attract talents. It's completely public that they are targeting like the fear of missing out of young engineers to convince them that the problems that are important for them are the problems that are most important for society. So you have this quote from Geoffrey Hinton from 6 years ago. 6 years ago, right at the peak of the deep learning hype, he said, and you can find the video online, we should stop training radiologists now. It's just completely obvious then that within 5 years, deep learning is going to do better than radiologists. So obviously completely false. And it was already pretty obvious to anyone actually working in medical imaging at the time. Personally, if I see a complete mutation of the work of a radiologist during my career, it's going to be amazing success. It's 5 years, it's ridiculously short as a time, and he said that obviously to market himself, to market his field, and also just to attract a whole generation of people. And when you go in a CS lab today, in a computer science lab, clearly the strategy has worked. Okay. Another thing is that tech companies, they want you to forget that fields are different from each other. And that's why there is so much focus on AI, so much focus on learning, because they want to merge to blur the difference between making targeted advertisements, making chatbots, and solving cancer, those kind of things. So this is a video that was recommended to me on YouTube 2 weeks ago. Welcome to DeepMind. So DeepMind, it's owned by Google, mostly in London, embarking on one of the greatest adventures in scientific history. And with quotes with like, our mission is solving intelligence to advance science and benefit humanity. And DeepMind, obviously, they do very interesting things. Obviously, the things on natural language, on proteins, it's great. I mean, there's no question about that. But I think you can take a bit of a step back and understand that, for instance, the hype about AlphaGo, the hype about the Go engine, it's really good that people are able to train those Go engines. But first, if you look at the papers, you see that it's not at all a transformer for natural language processing. Like the algorithm shares a lot of structural similarities with previous generations of Go solvers. So it's very much something that is designed for Go. And, like when we were children, Deep Blue bet Garry Kasparov, at chess, didn't change the face of the world. So, some of those projects are going to be very impactful, like for protein folding, for natural language processing, but that's great projects that have been designed by huge teams of very talented people. And I'm just telling you, you are very talented people. I think your choice has a lot of weight. You don't have to work in those companies to make something meaningful. It's really not the only thing. So, I'm just telling you, we're not blind. We see that there are tough times ahead for generation. And so it's a real question with your skill set, what problem are you going to solve? And you cannot solve all of them at once. It's not going to happen. So maybe you want to work on quantum computers, chess engines, on drones, because they're so effective in Ukraine, on efficient batteries, drug safety, nuclear fusion, machine translations. All of those are worthwhile projects. And personally, I think it's a bit of a shame that everyone's, or like 90% of the community, wants to work on the same two topics. I think we need to study a bit of everything. Okay, so, and I'm telling this to you because we are extremely lucky in France that first, we do not start our lives with a huge debt. And we have this social safety net where, if we get cancer, when we do not go bankrupt, all of that. I have friends in the US, I have friends in China. The situation is they are under much more pressure. So frankly, you have genuine freedom of choice. Or I hope so for you. So try to use it wisely. Okay. And so it's not something that I can do for you. You have to ask yourselves the questions. And I think this is the main point of the MVA. I started the MVA because I wanted to do applied math and that I liked essentially the class of Stefan Mahler on signal processing. That's what I signed up in 2015. Then I took many classes and I realized that I really enjoy medical things, medical imaging, because it was a good combination of what I love, because I have lots of doctors in my family. I really love this place, essentially. Like it's a very meaningful place, even Hôpital Cochin, for me. I was good at it, visibly. Clearly, the world needs that. And it's also a field where I could get paid very decent money. You know, it's a huge industry. I know that there are academic positions available, but also jobs in the industry. You know, I didn't sign up for poverty or precarity when I did medical imaging. So I think it's a balance, and try to find your own way. You know, and that's maybe the main spirit of this geometric deep learning field, is try to fill in the gap between purely data-driven methods and deterministic, let's say, physical or math-based baselines. Okay. So I think that's it for today. You know, important messages, I think. If you want to do, so we are not going to do a lab session today, but if you want to know a little bit more about it, so first you have references on my webpage and in the slides, and the PyTorch geometric library. I mean, it's really well made. It's really interesting. So if you just go through the tutorials of this library, I think you're going to learn a lot about what we do, what are the limitations also, etc.